So in this video we'll be proving proposition 4.60. Now let factor A be a commutative C-star algebra contained in the C-star algebra of bounded operators on a Hilbert space H. Then there exists a maximal abelian W-star algebra in L of H, which itself contains A. So this proof is going to be done using Soren's lemma. Now, the first thing you need to notice is that the commutative C-star algebras in L of H that contain A are partially ordered by inclusion. Now, for any chain in the partial order, note that their union is actually a self-adjoint commutative subalgebra of L of H. This allows us to use a result that we proved in video 6, which is that if you have a commutative self-adjoint subalgebra, then its closure in the weak operator topology is a W-star algebra, therefore a C-star algebra, which is an upper bound for the chain. Therefore, by Soren's lemma, we get that there exists a maximal commutative C-star algebra containing A. Now, applying proposition 4.47 on this maximal M, we see that it's contained in a commutative W-star algebra. By maximality, it is a W-star algebra, and that concludes the proof. Now, the following notion is of a considerable importance in any serious study of W-star algebras. So this is definition 4.61. Let A be a set of operators over H that don't necessarily even form a subalgebra. Then we define its commutant and denote it as A prime as being the set of all operators over H that commute with all the operators in A. So note the following fact. If A is self-adjoint, so we're only assuming that it's closed under adjoints, then its commutant is actually a W-star algebra. So this is another method of obtaining W-star algebras. And this is an easy fact to prove. Just consider a B1 and a B2 in the commutant of A, then we see that it's a vector space because of the following calculation, which just uses the fact that each of them commutes with A. Then to show that it's an algebra, we simply use associativity and commutativity for B1 and A and B2 and A. Now, to show that adjoints are in the commutant, it's a bit more interesting because we have to write A B1 adjoint in the following way and use the fact that A star is in A to have them commute. Now, for a limit in the weak operator topology of a net of operators in the commutant, we see that because precomposition and postcomposition with A are continuous in the weak operator topology, that A and B commute, therefore the commutant is a W-star algebra. Now, with the definition of a commutant, we can actually provide an algebraic characterization of maximal abelian W-star algebras. So to see this, let's take a look at proposition 4.62. A C-star algebra A of bounded operators over H is a maximal abelian W-star algebra if and only if it is equal to its commutant. So to start off the proof, we're going to assume that A is equal to its commutant. Then since A is a C-star algebra, it's self-adjoint, and by our previous remark, we have that the commutant of A is W-star. That is, A is W-star. Moreover, since each element of the commutant, which is A, commutes with each element in A, well, then we have that A is commutative. Now, if we suppose that A is contained in some other commutative C-star algebra, M, and we have an operator T in M, note that T commutes with every operator in M, and therefore commutes with every operator in A. Therefore, T is in the commutant of A, which is equal to A. Therefore, M is equal to A, and A is a maximal abelian W-star algebra. Now, conversely, let's suppose that A is a maximal abelian W-star algebra. Now, for an operator T in the commutant, we can write T as H plus IK, where H and K are both self-adjoint and in the commutant of A. So we've seen this trick before in the book. What we do is we take H to be T plus T star over 2, and we take k to be t minus t star over 2I. Now, since the commutant of A is a W star algebra, both of these are in the commutant, and they're clearly self-adjoint. So this is a typo, but I didn't want to fix it. Instead of A union H and A union K, you should have the subalgebras generated by A and H and A and K. And those are commutative because H and K are in the commutant of A, and they're self-adjoint. So then, by proposition 4.47, we get that their closures are abelian W star algebras that also contain A. So by maximality of A, we have that A is equal to both of these abelian W star algebras. Therefore, H is in A, K is in A, and we have that T is in A. Now, since C is an arbitrary operator in the commutant, we have that the commutant is a subset of A. Moreover, since A is abelian, then every operator in A commutes with every other operator in A. Therefore, A is a subset of its commutant. And that concludes the proof. So in the next episode, we'll be proving a quick result about the commutant for C-star algebras of operators on a Hilbert space.